All right, guys, we have been dealing with quadratics, with second degree functions and parabolas. We're going to extend that a little bit today and start talking about higher degree, so cubic and quartic and higher degree functions of all degrees. We're going to start with end behavior. You should know right now that a quadratic with a positive leading coefficient opens upward. So let's see, this will be degree up here. Positive, negative, a negative leading coefficient opens downward. Third degree, or cubic, positive cubic is going to look like this in general. Now, it doesn't have to have the peak and the valley. It might just level out, like x cubed just gets flat right in the middle and then keeps going up. But one way or the other, it's going down to the left and up to the right. All right, this end behavior. A negative is just going to flip-flop that. All right, it might have two turns, or it might not, but it will definitely go up to the left and down to the right. You get the idea here. 4, it's going to be the same direction. 4 has enough turns to make like a W shape, or a negative would make like an M shape. And like I said with cubic, like x to the 4th kind of looks just like a parabola, even though it's not. It doesn't have to use up its maximum number of turns, but it could. And this pattern continues. 5, degree 5, we've added another turn, negative degree 5, like this. So when we deal with higher degree functions, one thing is going to be to graph them, to figure out approximately what they look like. And end behavior is the first place to start. Now let's talk about possible roots. We're going to have combinations of real and imaginary roots. Let's say like a positive cubic. It might go like this. We might have 3 real roots. Positive cubic might have 1 real root, but it's at least going to have 1, because you can't go from bottom left to top right with it without crossing the axis at least one time. Quartic, 4th degree, it's got some options. Actually, I forgot one. With cubic, it could have 2 real roots and do something like this in blue, where it just touches the axis. We've got a root here, and then a root here where it touches the axis and bounces off. That's what we call a repeated root. And in the factoring process, like let's say that's 2, this cubic would factor to, let's call that negative 3, x plus 3, and then x minus 2 would be repeated root. We could write it as x minus 2 squared, or x minus 2 times x minus 2. But a repeated factor like that, that shows up in the graph as a bump, bounce off the axis, and then go the other way. So 4th degree could have 4, like that. It could have 2. Oh, that's going to have 2. Let me take that back. It could have 2 like this. All right, the 2 little dips in the W shape don't have to be on the same level. It could have none like this. It could have 1 if you did a little bounce off thing. It could have 2 if you did a repeated root like that. But possible roots, keep in mind, whatever the degree is, that's how many roots it has. Whichever ones are not real, that are not shown as an intercept, those are going to be imaginary. Those are going to be the ones with the eyes in them, and we'll be finding those. All right, the factor theorem. This is important for us, and I kind of just showed it in blue right above. Basically what it says is this. If a number a is a root, and this is for integers right now, the whole number a's, x minus a is a factor. So because negative 3 was a root up above, right here, x plus 3 was a factor. Because 2 was a root, x minus 2 is a factor. It happened to be repeated, but that's another story. Okay, so what this lets us do is factor higher level polynomials by knowing what the roots are. Okay, so if you can look at a graph of it and see what one root is, or if you're just given a root like we are below here, then you can factor it by factoring out that factor. Okay, so what that means is down here, all right, we're going to do a process called synthetic division. And our goal is to factor and to find the zeros, which basically means solve the equation. If I let f of x be 0, then I'm solving this cubic equation. Okay, so one factor, 1 0 has been given, and because of the factor theorem, what that tells us, x minus 2 is a factor. All right, so if you've got one of the factors, you can divide that out to get another one. All right, so if I tell you that the number 2 goes into the number 100, I can divide out that 2 and get 50 to see what's left over. And then if that 50 will break down further, then I go on and do that. So let's see what that looks like here. I know that f of x, if I'm trying to factor it, equals x minus 2 times another factor or 2. How do I know that? Because of the factor theorem. 2 is a 0, x minus 2 is a factor. So how do we divide out that x minus 2 from that polynomial? There's a couple of options. You can do old school polynomial long division, or you can do what's called synthetic division, which basically is the same. It just takes all the x's out of the way, does the math, and then puts the x's back in. So we're going to jump straight to that. We'll get to polynomial long division at another time. So here's how synthetic division works. My goal is to figure out what goes here. What is left over when I factor out x minus 2, okay? So I'm going to take that 0 of 2, all right? I know that this is a positive cubic, and it goes through 2. I'm going to take the 0 of 2. I'm going to write just the coefficients of the powers of x next to the 2, okay? So 1x cubed, 1x squared, negative 16x, and 20. And by the way, if there's a missing coefficient, like if there were no x squared term, you would use a 0 as a placeholder. Okay, here's how synthetic division works. Take the first coefficient and just drop it down to the bottom. I'm going to multiply that number by what's in the box. 1 times 2 is 2, and I'm going to write the 2 under my next column. Now I'm going to add. 1 plus 2 is 3. 3 times 2 is 6. Negative 16 plus 6 is negative 10. 10 times negative 2 is negative 20. And negative 20 and 20 makes 0. Now, in order for x minus 2 to be a factor, you have to get a 0 right there, all right? Basically, every time you're going to get a 0 there, as long as you're dividing out a true factor. If you don't get 0 there, one of two things is true. Either x minus 2 wasn't a factor, but we were given that it was, or you made a mistake in your calculations. All right, so look for zeros if, in fact, 2 really is. You look for a 0 remainder, that's the remainder spot, if, in fact, 2 really is a 0 and x minus 2 really is a factor. Okay, so my question was, what goes in that other set of parentheses? And here's the answer to that. The first, I've got 0 remainder. My constant term is negative 10. My linear term, or my x term, is 3. My quadratic term is 1. So this is x squared plus 3x minus 10. All right, so I have done some factoring. Okay, remember the number 100. If I tell you that 2 goes into 100, I take out a 2 and I'm left with 50. Now that 50 may or may not break down. We know that 50 could break down a couple of ways. So it's possible that this quadratic can break down further. All right, so you just look at it and try to factor it. Can we break it down into 2 linear terms? All right, so are there 2 factors of negative 10 that add up to 3? All right, and they are plus 5 and minus 2. So we factored it down even further. One of our goals is to factor it and then to find the zeros. Okay, so here's the factored form. Here's one answer. The other answer is, what are my zeros? Okay, well, one of them is 2. I was actually given that one. But what we want to do is do 2 multiplicity 2, meaning I know that 2 is a 0, but it's also a repeated root. It happens twice, and my other one's negative 5. So that mult is it's called multiplicity which just basically tells you how many times that factor of x minus 2 shows up in the factored form. So just quickly, this graph, if we were going to sketch it, it has a 0 at -5, and it has a 0 at 2, and that's a repeated root at 2. So it's going to act like this. Remember, it's a positive cubic, so without too much detail, it's going to look like that. All right, and its y-intercept, by the way, would have been 20. So I'm a little off on my scale here, but let's call that 20. So we can get a decent idea of the picture. All right, so quickly, one more example. I'm given a cubic. I'm given one of the zeros. So -5 is a 0, which means x plus 5 is a factor. To figure out what the other factor is, I'm going to put the -5 in the box. I'm going to put the coefficients out next to it, leave a space, and draw a line. All right, so I'm going to encourage you to pause and do this synthetic division, especially if this is new, and then resume and see how it goes. All right, so I'm going to drop the 1, multiply -5, I'm multiplying by the number in the box, add and get 2, multiply and get -10, add and get +10, multiply, get -50, get that 0 that I'm looking for. And now factored form looks like this. X plus 5 times x squared plus 2x plus 10. All right, so here's where I was on the last time, and then I factored the quadratic that I got. So I need to look at x squared plus 2x plus 10 and see if I can factor it. All right, and it's not going to take me long to realize there are no two factors of 10 that add up to +2. So I cannot factor that anymore. So factored form, that's it. But what about find all the roots? What are the three solutions to the equation if f of x equals 0? I know -5 is one of them already. There need to be two more, and those are going to be the two solutions to this quadratic. Okay, so how are those found? Quadratic formula. So I've got x equals -5. Let me find the other two. (b) plus or minus square root of b squared minus 4 times 1 times 10. That's 4ac all over 2a, or -2 plus or minus, let's see, that's 4 minus 40, it's -36. All right, so that's at least a perfect square number if it's going to be imaginary. So we have -2 plus or minus 6i over 2. And since 2 goes into all three of those numbers, -1 plus or minus 3i. All right, so the second part of this question is, what are the solutions? What are the roots? They are -5 and those two imaginary. Okay, imaginary solutions always come in conjugate pairs. A conjugate pair looks like a plus or minus bi. So here's one of those. -1 plus or minus 3i. They're not opposites. It's not one of them is negative of the other. It's the imaginary part is added and subtracted in the pair. The -1 is staying as -1. So those always come that way. And actually, if you were given one of the two, you can automatically know that one of the roots is its pair. They always come in partners. So lastly, what does this graph look like? It's a positive cubic. It goes through -5, and it has two other imaginary roots. So just to sketch, -5 is here. Y-intercept is 50. So this will be off of scale again, but it's going to come up. It has to go down left. It's going to come up through -5, and it is going to not touch the axis again. I guess technically it could have gone like that as well. I'm not sure, but what I do know is that its only real zero is -5. The other two zeros are imaginary. All right, so that's the main skill of the day, factoring and solving cubics using the factor theorem and synthetic division. All right, so that's what we'll be working on in class. See you then. Young out.